So this week you're going to be identifying the unknown metal using specific heat and density. So in talking about specific heat, there were a few different variables that we had that were similar to specific heat. One of them was heat capacity, which we've defined as this capital C. It's the amount of energy required to raise the temperature of a particular object by 1 degree Celsius. It's an extensive property, so it does depend on the amount of substance that's there. A lot of times when we've used heat capacity, that's been in terms of a particular calorimeter or some object that we're familiar with. So that's typically why we would use those units. Another one is molar heat capacity, which is C sub m. This is the amount of energy required to raise the temperature of 1 mole of that substance by 1 degree Celsius. So for example, the molar heat capacity of water is about 75 joules per mole times degree Celsius. This one is intensive because you have moles being accounted for in the unit itself. Oftentimes we're interested in this because different things have very different molar masses. So a lot of metals actually have pretty similar molar heat capacities, though they don't have very similar specific heat capacities, which is what we're ultimately going to talk more about. This one's also intensive. So a specific heat capacity, which is C sub S, sometimes you'll see it written as capital S. I tend to not like that as much, but C sub S is the one that I see probably more frequently. And that's the amount of energy required to raise the temperature of 1 gram of that material by 1 degree Celsius. So the specific heat capacity for water is 4.184 joules per gram times degree Celsius. So again, that means it's going to take 4.184 joules to raise 1 gram of water 1 degree Celsius. So that's what this ultimately means. If you have a lower specific heat capacity, it requires less energy to raise the temperature of a particular mass of that material. So we're familiar with water. We've seen that before, 4.184. But these are for a particular substance. So you have to be concerned with what substance you're referring to. So we're going to actually use this particular property to help us identify what metal it is we are using in our experiment. This is what our experiment's going to look like. Remember, the change in internal energy equals heat plus work. This is a calorimeter. It's a coffee cup calorimeter on the right-hand side here, where we just have 2 nestled styrofoam cups that are going to be our insulating materials there. We're going to be measuring the temperature of that water as we go. But for a coffee cup calorimeter, we assume that there's constant volume, which is a good assumption. So the work ends up equaling 0. So it means that we can really just focus on heat. And there's going to be some heat transfer. Let's say we just define the metal cube. So you see there's a metal cube in the coffee cup calorimeter. We're going to assume that is the system. So we're defining the sample as the system. This is the metal. And then the water, all of the water in here is the surroundings. I know technically the surroundings would be everything, but we're assuming that all of the energy is transferred between the system, which is the metal cube, and the surroundings, which is water. So there's going to be a heat transfer between the system and the surroundings. So the Q of the system, the heat of the system, needs to equal negative heat of the calorimeter, which is our surroundings. So that will be what we are measuring with the thermometer as it goes, and that's the water surroundings. Maybe you remembered Q equals mc delta T. So that's the mass times the specific heat times the change in temperature. That equals the heat for that particular item. And we'll be able to deal with that in terms of both the systems and the surrounding. Remember, anytime you see a delta, so delta T, that's T final minus T initial. So the final temperature minus the initial temperature. So we can use that as well. An important note here is that the final temperatures are going to be the same for both substances. As time goes on, they will equilibrate in their temperature. So that will be a helpful metric. So if we plug in some of these variables, if we can kind of substitute Q of system equals negative Q calorimeter and substitute in mc delta T for each of these, this is what we would end up getting, right? So you have the mass of the system times the specific heat of the system times the change in temperature of that system should equal negative mc delta T of the calorimeter. And this was all for the water. Again, remember T final minus T initial. The T final is the same for both substances, so we can substitute T final in there. T initial of the system is going to be the initial temperature of our metal cube, and the T initial of the calorimeter is this water at roughly room temperature. What should be noted is the way that we're heating up the sample, that metal cube, which I'll show here in a second as well, what this actually looks like. We're going to be boiling water and putting the metal cube essentially inside there. It's not touching the water, but we're going to have two different temperatures of two different water baths. We're going to have a boiling water bath, and that's actually the initial temperature of our system. We're assuming that the cube of metal will end up being the same temperature as that boiling water, but the temperature initial of the calorimeter is not the boiling water, it's the water at room temperature that's sitting inside the calorimeter. So it's a little confusing because we have two water baths essentially. One that is used to heat the metal cube, the other that is just the initial bath for the water, the initial calorimeter temperature. So this is the system that we can have set up. And again, we can substitute in what we mean by system and surroundings. So system and calorimeter. We have the mass of the metal times the specific heat of the metal, which is ultimately the unknown, right? That's the only thing that we're not going to know. So we can solve this for the specific heat of the metal. We're going to have the mass of the metal. That's what we start with, depending on the trial. The T final, again, is the same for both the metal and the water. We're going to have an initial temperature of the metal. Again, that's going to be the way in which we got that was how the boiling water. So it'll be roughly 100 degrees Celsius. It won't be exactly 100 degrees Celsius, but it'll be roughly that. We're going to know the mass of the calorimeter. That's the mass of the water in here. The specific heat of water, we're assuming that this is pure water, which it is, very roughly, right? So that is the 4.184 joules per gram times degree Celsius. And again, T initial of the water will be roughly room temperature, and the T final will be whatever our final thermometer calorimeter measurement comes to. So we're going to be able to use this to get to the specific heat of the metal. And you'll have some data that you can deal with in calculating these. So this is what I had mentioned before in terms of how we are heating up the metal cube. So this is boiling water. It'll be roughly 100 degrees Celsius. We're actually measuring that. We would actually be measuring the water's temperature. So maybe it's 99 degrees Celsius or something like that. And then here we have a large test tube, and there's no water in that test tube. The only thing that's in that test tube is the metal cube or metal, your metal sample, however much mass of metal you have. And you would leave it in there for a long enough period of time, let's say 15 minutes, a long enough period of time for that metal to heat up reasonably to be about the same temperature as the water surrounding it. So that's how we're heating up that metal. So this is actually how we're going to get the temperature initial for our sample, or the temperature initial of our metal, right? So this is what that setup would look like. All right, you can follow this link to access a simulation that's actually pretty good that goes through how you would be doing this. I know we had a few photos and all of that can be a little bit helpful, but there are a lot of variables to deal with. I would just really stress, make sure that you're labeling these. You can't just say mass. We need to know if you're talking about the mass of the metal or the mass of the water, for example, right? Same thing with temperatures. We can't just be labeling temperatures. We want to know if we're referring to the temperature of the metal or the temperature of the calorimeter, meaning the water temperature, so on and so forth, right? So be really careful with that. You can click on the experiment tab, run the demonstration. There's some on-screen directions, answer those questions. That will give you some good understanding of the experimental setup that we would have used if we were in person. And then, like normal, we have the same. We'll give you data here that you'll be able to use. So this is the unknown data, or the unknown data is on the next slide here. So you'll first determine the specific heat of your unknown metal based on the data that I'll give you on the next slide. Then determine the density of your unknown metal. We're already familiar with how to do this. We'll get some information about mass and volume. And I think we know how to go about getting density from that sort of information. And then you're gonna need to justify what unknown metal you have chosen. This is that same list you saw before. This is in your packet, so you can use that table in the lab write-up to help. You really need to compare your answers to what I've called the literature values. These are the literature values, right? They're the values that are known for a particular substance. So you're going to need to compare and contrast that to make sure, you'd list how many things had similar densities and how many things had similar specific heats, and it should probably only overlap with one material, and that material is the one that you would then pick for your unknown. And so you need to kind of justify that as best you can. You can't just say at the end, oh, I determined that my unknown was cadmium. You need to have some indication of how you knew that, especially when it comes to writing the abstract and results section. Okay, so here are your unknowns. Only use one unknown. I've assigned you one of these unknowns. And you can pause this to take a look at all of that, and this will be how you start your packet.